Today we will talk about probability distributions of random variables. We begin by let S be a sample space of an experiment and a random variable x, which is a function x that is going to be from the sample space S to the set of real numbers. The values of capital X, that is denoted by script X, will define a new sample space for the original experiment. X or script X extracts some specific information about an outcome in the sample space. Let's work out some examples to get a hang for what is going on here. So we will describe an experiment, a random variable, and some sample values for the random variable. So suppose we toss a coin 5 times, then a random variable could be something that counts the number of heads in a given five tosses of the coin. We could get random variables to take the value 3 or 1, depending on whether the outcome is HHTTH or HTTT. We could also consider a random variable that calculates the proportion of heads in an outcome. In this case, the random variable is going to take the value 3 over 5 for the outcomes HTTT, H, and HHHT, T. Similarly, the random variable is going to take values 1 over 5 for the outcomes HTTT and THTTT. We can also consider the experiment where we roll a six-sided die 4 times. In this case, the random variable that calculates the sum of the numbers that face up would give me values 11 for the sample 1244, the value 9 for the sample 1116, and 20 for the sample 6662. We could also consider a random variable that calculates the average of the numbers in this sample. In this case, we will get values for the random variable to be 11 over 4, 9 over 4, and 20 over 4 for each of these respective outcomes. We could consider a third example where we choose a box of milk cartons. A random variable in this context could be calculating the weight of the box. Depending on what box we choose, we would have different weights for the boxes that we have chosen. And we notice that in this case, the values of the random variable could lie in an interval inside the set of real numbers. Note that given an experiment with sample space S and a random variable x, a function from S to R, we now have two sample spaces to work with: the original sample space S and the new sample space script X, which is the values of X. For simplicity, let's assume that the cardinality of the sample space S is finite. In this case, we list out the elements of the sample space. And if X is a random variable, we let the values of X to be listed out as X1, X2, up to Xk. Now, the two sample spaces for the original experiment are script S. This sample space has simple outcomes given by the SJs, where J's go from 1 through n. On the other hand, script X has simple outcomes which are of the form xi, where I goes from 1 through k. A simple outcome for the sample space script X is going to be given by X equals xi, which is the set of all simple outcomes in script S, such that X of S equals xi. This is a subset of script S. We note that an event in the context of the sample space S is going to be defined in terms of the simple outcomes Si's, whereas an event in the sample space X is going to be described in terms of the simple events x equals xi. Now let P be a probability function for the sample space S. We will now use P to induce a probability function Px on the sample space script x. The first step in this process is going to define Px on simple outcomes as the sum of the probabilities P omega for omega inside the outcome x equals xi. The next step in this program is to define a P of x for an event E subset of script x. The event E is going to be a disjoint union of sets of the form x equals xi, and Px of E is going to be defined as the sum of Px equals xi, which we have already defined in step 1. We set up some conventions. The random variable will be denoted by uppercase letters x, y, z, etc. And the values of the random variable will be denoted by lowercase letters, that is small x, small y, small s, small z, all lowercase letters. Also, when there is no ambiguity on what the probability distribution is, we will use the notation p x equals xi interchangeably with px of x equals xi. We next talk about distributions of random variables. Let x be a random variable and p sub x be the probability function for x. In this setting, the cumulative distribution function of x is going to be a function capital X sub x, and it is calculated by computing the probability p of the event x less than equal to small x. We write it down precisely as follows. Let's work out an example. Suppose we toss a coin 4 times and we set the random variable x to count the number of heads in 4 tosses. We can then calculate the probabilities of the simple events in script x, which are going to be calculated as 1 over 16, 4 over 16, 6 over 16, 4 over 16, and 1 over 16 for each of the simple outcomes respectively. And we can use this information to calculate the cumulative distribution function f sub x of x using the definition defined above. We can plot the cumulative distribution function into over the set of real numbers, and we notice that the cumulative distribution function is going to have a bunch of jumps, and each of these jumps are going to be corresponding to the probabilities of the simple events. We make a few observations about the cumulative distribution function in this example. Notice that the jumps occur at x equals 0, x equals 1, 2, 3, and 4. And each of these numbers are exactly the simple outcomes inside script x. Also notice that f sub x is a non-decreasing function, and the limit as x going to negative infinity of f sub x of x is going to be 0, and the limit as x going to infinity is going to equal 1. Furthermore, f(x) is going to be greater than equal to 0 for all values of x. Every CDF satisfies properties 2, 3, and 4, and in fact, these would help us define a general CDF. So we state a theorem which states that a function f of x is going to be a CDF if and only if we have the following three conditions to be satisfied. The first being that the limit as x goes to negative infinity of f of x has to be equal to 0, and the limit as x going to positive infinity of fx has to be equal to 1. Fx has to be a non-decreasing function, and fx has to be right continuous. That is, the limit as x going to x plus fx is going to be equal to f of x0 for all x0 inside R. With the definition of CDF in our toolbox, we are ready to classify random variables broadly into one of two types. Given a random variable x, we will say that x is discrete if the cumulative distribution function of the random variable x is a step function. We say that x is continuous if the cumulative distribution function of the random variable x is a continuous function. When we're working with discrete distributions, we will have a probability mass function p sub x of x, which is going to be defined as the probability of the simple outcome x equals x for all values of x. For continuous random variables, we define the probability density function as the function f sub xx, and the function satisfies that the cumulative distribution function is the integral from negative infinity to x of fx t dt for all values of x. We finish up by describing all probability density functions, which would be functions that satisfy the two properties that fx has to be greater than equal to 0 for all values of x, and the sum of fx x equals 1, or the integral from negative infinity to plus infinity fx x dx equals 1, depending on whether fx corresponds to a discrete random variable or a continuous random variable, respectively. To summarize, we have spoken about inducing a probability function on the sample space script x. We have described the cumulative distribution function of a random variable and the probability density function of a random variable. We will be visiting these concepts a lot over the course of this video series. For now, this is all. Take care of yourselves, and I will see you around.